So getting started, the general idea is that if we have an input to our system, then we might have a sensor, which is a reference sensor. And this sensor is taking this physical uh, property and then typically creating some sort of voltage. And we would take that voltage, and typically we're going to subtract off some other voltage being generated that we're measuring. And so then that means that there would be an output sensor, typically in the feedback loop, and that would feed into our controller, which then generates the command to some sort of actuator, which could then have a disturbance added into it, which then finally all of that goes into the actual plant. The plant is actuated, and there's some sort of output generated, and that's the thing that gets measured in our output sensor. Now, we've been looking at this kind of architecture throughout the class, and this is again our way of doing algebra. So we have typical elements, and we've looked at two of those so far. We have the sum junction or comparator, and we're comfortable with the idea that this generates inequality in the sense that everything going in has to add up in some way to get the signal that's coming out. Or I could have a minus sign. So in this case over here, here's our comparator, and I've got voltage in minus voltage out equals, and typically we would think of this as an error that we're generating, right? And we've been doing this. So in this case, this would be, say, R of t, which has a Laplace transform of R of s. This might be y of t that we're measuring, which also has a Laplace of y of s. And then by definition, the output of the comparator, we'll call it the error, is equal to the difference of the reference input minus the measured output, and we can take the Laplace of all of that, and so then the error in the Laplace domain is just the difference between the reference and the output in the Laplace domain. And again, we can have as many pluses and minuses that we want here, and we could add accordingly. The important thing about all this block algebra is that we can think of all this happening in the time or in the frequency domain. So the product, so here's your sum junction. The operator, or the product or operation block, is one thing we've been using as a gain, right? We've been in MATLAB, it's like this, and this little triangle. And if there's an input signal, say u of t, and an output signal y of t, and again, these can be in the Laplace domain. And this works because of the linearity property of the Laplace, that the Laplace of the k times u of t is equal to the Laplace k times the Laplace of u of t, which is just k u of s. Right, so this tells us then that u of s is equal to k times y of s, right? But we can also have a more sophisticated operation where we actually operate with a derivative or something like that. But when we go into the S domain, then we typically end up with systems that look like the following. If I have u of s, I can have a block here that is, say, g of s, and I have an output here, y of s, and I just do multiplication. All right, and again, this is the value of the Laplace domain, is that a differential operator becomes a multiplication, right? So instead of taking derivatives, I take products of s once I'm in the Laplace domain. So this tells us that y of s is just g of s times u of s. Order of operation can be important here, all right? And typically, this the way this works, not just typically, but always, the way this works is that g of s is first times u of s. So it's whatever is in here times this guy. When the systems are linear, obviously order of operation isn't as important, but there are times, especially in Simulink, where order of operation is very important. So this product or multiplication is important. There's just by way of example, we can look at two different cases. If I have things in series, right? In other words, let's say I have U of S, and I have G1 of S, right? And then multiplied, let's say call that A of S, and then that's multiplied by G2 of S, and that's then equal to Y of S. I can just apply the rules, and so now I have that A of S is equal to G1 of S, U of S, and I have Y of S is equal to G2 of S, A of S. So I substitute in A of S into there, and I get that Y of S is just equal to G1 of, G2 of S, G1 of S times U of S. All right, and a lot of times we can leave the S's off, all right, to make our lives a little easier. So series is like multiplication, right? As we would expect. All right. I can reduce this in the sense of reducing this down to one block by saying that U of S then feeds into G1 of S times G2 of S, and then out comes U of S. Out comes Y of S. So this idea of block diagram reduction becomes useful when trying to collapse a bunch of different blocks down into one block. Another example is if I have things in parallel. In other words, here's series. Here, let's look at parallel. Let's say I have U of S coming in, and I have two block transfer functions, G1 of S and G2 of S, and this signal splits off and multiplies each one of those, and then these two come back together and get added up in a comparator, and the output here, say, is Y of S. Call this A1 of S and this A2 of S. So what we see then is that from the multiplies in G1 and G2, then A1 of S is just G1 of S times U of S. A2 of S is G2 of S times U of S. And from the comparator, the output Y of S is just the sum of A1 of S and A2 of S. So making substitutions, I find that I have G1 of S plus G2 of S, and then that whole thing gets multiplied by U of S. So when things are in parallel, it's like they're being added together. Another interesting case that we're going to start to look at a lot is the idea of a feedback loop. And we can represent this in a fairly general way by saying I have the reference input, R of S, and there's my comparator. I go through some transfer function, this is called the forward loop, and out comes Y of S, and then take the feedback through some transfer function, call it H of S, and feed that back with a minus sign. So this is negative feedback. And these transfer functions can be anything, any rational polynomial in S. And so the way to analyze is say, let's call this, P of S or something like that. So I can write down the following. I have Y of S, right, is equal to G of S times whatever's going into here. Let's call that E of S. So there's E of S right there. Then I can write down that P of S is just H of S times Y of S. And finally, I can look at the comparator and say that E of S is just R of S minus P of S. So with these three equations, I can make substitutions and solve for one block diagram. In other words, I want to reduce this to R of S going in, one block right here, and then Y of S coming out. Right? And this would be the closed loop block or reduction. All right, so just making substitutions, I then have that Y of S is equal to G of S times E of S, which is now going to be R of S, and then I need minus G of S times P of S. Make the substitution for P of S, so I have G of S, R of S, minus G of S times P of S, which is H of S times Y of S. Collect the Y's all on one side, and so I then have Y of S plus G of S, H of S times Y of S is equal to G of S times R of S. Factor out a Y and divide. In other words, I end up with Y of S times 1 plus G of S times H of S is equal to G of S R of S. And finally, solving for Y of S, I end up with G of S over 1 plus G of S times H of S. Alright, there's my phone. Times R of S. And I could divide through by R of S, and this is referred to as the closed loop transfer function. Alright. G of S by itself is referred to as the open loop transfer function. So when we talk closed loop, we're talking about what's the transfer function from the reference input R of S all the way to the output Y of S, given there's a feedback loop in the system. That would be the closed loop transfer function, and it is this block diagram reduction of the whole system down to one block. If another definition here is that if H of S is equal to 1, so it's just a scalar 1, so there's nothing happening to the output, just being multiplied by 1, then we call that a unity feedback loop. All right, and it makes sense because unity here refers to 1, and so it's just being multiplied by 1. So it's not being filtered or scaled. The other thing to notice is that if we had positive feedback, so if the comparator had a plus sign on both sides, so it was up here it was plus and then plus, then notice that what that does is change this sign right here, and the net result is that I end up with Y of S over R of S is equal to G of S over 1 minus G of S H of S. All right. Typically we see negative feedback, not positive feedback, but we could do either case.